All right. So today we are going to talk about a few important properties of the etho diffusion process. So we have been using the etho diffusion process a lot in all our continuous time modeling. This was our canonical model right here. This dxt equal to bdt plus sigma dw. And if you are interested in physics or physical properties of these kind of structures, then this is the random movement of a particle model, where B is called the drift coefficient and sigma is called the diffusion coefficient. So in physics, we call it drift and diffusion. In finance, we call it trend and volatility. Doesn't matter. Same model, similar analysis. And then we have developed our Black-Scholes starting from this. In the way, we have also developed the etho calculus, learned a little bit about the etho process, etho's lemma, and other things. So now that those things are more or less done, I will essentially conclude the course. So I think today will be my last lecture. There will be a few more special lectures, of course, that are coming up, but I think my teaching will be done today. So this diffusion process or the etho diffusion process has a few very important properties. We will talk about them today, and we will see how these things relate with our understanding of the normal distribution, because it should have some kind of intuitive connection, and also why these properties are important to study. All right, so let me begin with what is known as the generator of an etho process. So what is the generator? So what is the idea? So whenever we talk about a differential equation, we normally look at either closed form solutions or approximate solutions, which are essentially based on Taylor series type arguments. So we may call it Taylor series, we may call it some other series, but the idea is basically you have infinite expansion, and then you show that after a few of the first terms, the rest can be safely ignored. That's how we normally work for any function which is reasonably well behaved. For our stochastic version also, we have seen that through arguments like the characteristic function or moment generating function, we have similar limiting results. Those limiting results give rise to probability distributions. And of course, expectation and the variance, these two play fundamental role, because after all, our model is normal distribution model. So first two moments. So the generator of an etho process is essentially the model of the rate of change. So this is called the generator or the infinitesimal generator, which is denoted by this symbol capital A. So capital A of a function f of x, where x is our etho process, that is defined as the limit when t goes to 0. Actually, t goes to 0 from above. Of course, it cannot go from below. The limit of this ratio. So expectation of fxt minus fx by t, where this small x is the initial value of the process xt. So x0 is essentially small x. So this symbol, first of all, we need to understand that it makes the right kind of sense. Of course, expectation is a deterministic function of time, so this ratio is a meaningful ratio. Then we need to understand whether this limit actually, the limit actually makes sense. Okay, so of course, good things don't happen all the time. So we need to first see what are the good functions f for which such limits will exist. So we try to define the set of good functions again, the set of functions f which are real to real, real valued functions such that this limit exists is denoted by capital D sub A of X. The sub A is for the generator and X is to denote that the function starts from small x. So the stochastic process, the initial value was at small x. So dAx. So this is our set of good functions. And now, of course, if we want to have a generic set of good function, then this has to happen for all possible x. Wherever I may start the process, I should still make sense of this limit. So the final set of good functions is essentially the intersection of this dAx over x belonging to R. So I have dAx for a specific x. So if I take the intersection over all x in R, all the possible starting points, then that set is the set where this limit exists for any starting point, which I call simply dA. Okay, so is that all right? So I'm trying to understand this rate of change operator in the expectation, which we call the generator, and I am specifying that the good functions for which this limit exists, that those good functions are collected in a set D sub A. So here is a result. So this result is again an application of Ito's lemma, where we want to understand how the existence of this generator can be related to the form of the generator. So of course, knowing that it exists is very well and good, but usually, is there a question, Ravi? Any questions so far? Okay. So existence is of course important, but typically we also need a little bit more, like how the form looks, exactly how computations can be done. So this lemma helps us with the help of the Ito process to give us an explicit formulation for these transformations. So let me make it precise. So let's suppose yt super x be an Ito process of the usual form that dy is uds plus bdw. We write here in the integral form and say that yt omega is x, where this super x is to denote what is the starting point. So this process starts at small x. So that's why we write this superscript, and the process in general at time t will be given by x plus this ds integral and the vdw integral. So for an Ito process, the first question would be, okay, so what is my set dA? Now this result says that let f be in C2R. So f is sufficiently smooth. So C2 is, the second derivative is continuous with a bounded support. So f must be sufficiently smooth, must have a bounded support. U and V, which are starting at small x, of course, because at time 0 there the process was at small x. So U and V are also bounded. So I have a transformation f which is C2 with a bounded support, and U and V are bounded. Of course, we know why boundedness of U and V are important, because I want to keep these integrals finite for all ranges and so on. So then I can explicitly compute the generator. My generator can be explicitly computed. So I compute this expectation, because this expectation is the first part in this ratio here, and then I will talk about the limit. So this expectation of fyt starting from x, so yt started from x, will be given by fx plus expectation starting from x of this expression within third bracket, and you can now recognize this expression as the usual expression coming from the ethos lemma from the dt component. The dw component we can safely ignore, because if we take expectation, that will give us 0, and if the functions are bounded, then it is no problem. The dt part, this will be the expectation according to the ethos formula. And we must remember that the expectation has to be calculated with respect to the natural probability law for yt. So we are not yet transforming any of the probability distributions to a market probability or other things. We are simply taking the natural probability law for y. So I have this explicit expression for expectation of f, which then will help me in finding the expression for the generator. And in the process, this lemma also says that the set dA is not very small, because as long as I have a C2 function, f is a C2 function with a bounded support, I am good. So this is my set dA. So I have quite a lot of functions available to me. And then the expression for expectation is given by ethos lemma. So this is the actual result, that if X is an ethos process and f is C2 bounded support, then f belongs to dA. So dA is basically the whole of all of this. And AFX, this generator AFX, if you now substitute for this expectation here by this expression, you can figure out that if I take the limit, that limit will work on this integral here. And again, we will use usual arguments of linearity and conclude that my generator will be bx del f del x half sigma square del 2f del x square. So you can write it in terms of uv or in terms of b sigma. So, but this is the more popular version, because usually the ethos process is written as bdt plus sigma dw. So what have I done? I have tried to define something called a generator of an ethos process, which is basically a rate of change of the expectation. The expectation expression for smooth functions, we know how to compute using the ethos formula. That's what we have done here. And in the process, we have also understood what are the admissible functions f. Using that expression and doing the usual limiting arguments, because I have to take this expectation here, cancel fx. Fx will be cancelled. And then this expectation by t, I'll have to do the limit. So that will lead me to the expression here as b del f del x plus half sigma square del 2f del x square. And of course, this is the first part of the ethos formula expression. So is this clear so far?
Sir, in this theorem, we require f to be bounded.
We require f to have a bounded support, and we require f to be sufficiently smooth.
Yes, but in this theorem statement, there it is not written f to be bounded. So is there any kind of...
I mean here,
Yes.
in this theorem statement?
Yes.
No.
So,
this theorem statement is not a complete statement. So all the earlier restrictions from the lemma, they will have to be translated here. So it is written slightly informally.
okay. No, I was thinking that there could be some kind of monotony MCD type of argument. So
We will need an MCD type argument.
yeah, because we can just consider this if fn equals a minimum of f and n, and then take the limit as n goes to infinity, and
that will be slightly complicated, because the limit on f directly is hard. Remember that function works on probability distribution. So that limit will be slightly complicated.
Okay.
You see, doing limit along with the expectation operator is fine, because then we are talking about deterministic functions, and I basically restrict the nature of the function. But if I want to do the limit directly on a random variable, then we have to understand what we mean by that. There exist such things, of course, but it will be more complicated objects. Is that what you were asking, or did you have something else in mind?
No, no, sir. What do you saying? Yeah.
So I guess you do know one or two candidates for those kind of derivatives, right?
Yes.
Yes. So, but we are not going there right now. We are sticking to the trusted ethos lemma and working with the expectation.
Okay.
All right. So my theorem is, this is not a full complete statement. So basically I have to put in the conditions from the lemma also. But the basic expression will be like this, which is again very much picked up from the ethos formula, first part. And this is called the generator of the ethos process. So often what happens is, when we want to express the ethos transformations on diffusion processes, we tend to use shorthands. And this generator is a very common shorthand. And if you look at this generator closely, whenever we are able to set up a differential equation, not a stochastic differential equation. Remember, to set up a differential equation in this context, we need to eliminate the dw term. So whenever we are able to do that, the differential equation will involve this generator. For a Black-Scholes model, it will be a simple, straightforward expression. For other more complicated contracts, if we are able to set up such a differential equation, we will again have some form of the generator. It may look more complicated, it may be implicit, etc. But this generator usually works as the building block for those differential or partial differential equations. Because often we see, even in this case, the Black-Scholes itself is a partial differential equation because there are two arguments. And the generator result actually can be rewritten in an alternative form. So this is our original expression here, the expectation expression. And I know that I can actually write this inside in terms of this generator symbol. And that representation is known as Dynkin's formula. So Dynkin's formula is just this expectation formula, where the expression inside, which we got from ethos formula, that we shorthand by using the generator symbol. So expectation of fx is fx plus expectation of integral af ds. So now this looks very much like our Taylor series. So this is as if we are just working with a first order Taylor series approximation. Of course, the similarity is not that straightforward, because we have to go through the ethos formula and the corresponding justifications. But Dynkin's formula is a popular result because it looks very, very familiar. So this is the first set of results, the Dynkin's formula and the generator. So before we move ahead, let us just look at a few simple examples. These are really, really simple, but sometimes these examples are essentially corresponding to forward equations for futures or call options like that. So like this one here, if I take dxt equal to only dwt, which means b is 0 and sigma is 1, then my generator is just half del 2f del x square. And this is a very common PDE, very common partial differential equation, and can be solved directly by analytical methods. A second example, so let us, as I said, we can always extend the ethos diffusion and ethos integral definitions to more than one dimension. So this is just one small example of such a situation, two-dimensional situation. So if I think of X as consisting of two components, X1 and X2, where X1 is driven by only a trend, so there is no randomness in X1. So you can think of X1 as the bank process, and X2 is pure diffusion, dx2 is dwt. So then dx can be written as bdt plus sigma dw, where b is the vector 1 0 and sigma is the vector 0 1, right? Because the first row has no dw and the second row has no dt. So b is 1 0 and sigma is 0 1, 2 by 1. So with that dx, the generator again can be written as del f del t plus half del 2f del x square. So if you just work out the formula from here, this one, we will easily see that the generator of this two-dimensional process will again be given by this very simple expression. Did you check this? So I am not doing the details, so I expect you to just do a little bit of writing and confirm that this is correct.
Yes, sir.
This looks right?
Yes, sir.
Yeah.
Right.
Okay, so this is the generator and the Dynkin's formula. So these are two of the properties which are essentially related to the expectation calculation, so that we can study the rate of change for the expectation. This rate of change is usually an important quantity. That gives us the formula, the theorem, and also gives us the Dynkin's formula as an alternative expression. And we have just seen very simple applications, but if you look at more complicated processes and contracts, you can figure out exactly how to compute the generator for such contracts. All right. So now let me move on to the other result, which is actually a very, very, very important result because it's extremely useful. This is an extremely useful result, and once we discuss it, we will see the connection with something which we have been using from our first year. In our standard probability and statistics work, all the time what we do is we assume models with normally distributed errors, and for calculation purpose, we always try to transform that normally distributed random variable to a standard normal random variable. So basically convert it to a normal 0, 1 random variable. And we know how to do it. We subtract the mean, divide by the standard deviation, we get a standard normal. So the stochastic process or the Ito process version of that standard normal transformation is called Girsanov's theorem. So Girsanov's theorem essentially tells us how to do this transformation, and two things. First, we must guarantee that through that transformation we are still having a normal distribution, and secondly, how the probability law has to be transformed. Because if we are transforming the random variable, the probability law will transform, and that expression must also be explicitly available to us. So that is what the Girsanov's theorem will do for us. Okay, so this is the setup. So let us talk about this setup, and then we will see how it relates. So let us start with some process, Ito process y, given by this expression, dy is beta dt plus theta dB. So beta is the drift, theta is the diffusion. Usual assumptions hold. This is my Ito process. Now, suppose I can somehow find two related processes, U and alpha, again from our good set, remember capital V was our good set, such that theta u is equal to beta minus alpha. Or you can basically rewrite it as u equal to beta minus alpha by theta, just to understand the connection between the standard normal result that we talked about, mentioned earlier, and this particular situation. So basically we find u and alpha such that u is beta minus alpha by theta. So that's somewhat similar to the normal, standard normal operation. Of course, we cannot have any u, alpha, etc. We have a little bit of restrictions. We have to assume that u is such that expectation of this exponential is finite. So I look at e to the power half 0 to t u squared ds. So normally for the good functions capital V, we insist on the integral u squared ds expectation to be finite. Now we are asking for something more. We are asking for the expectation of the exponential of this thing to be finite. So it is a stricter restriction, right?
Yes.
So that we will see why we need that, but we need to restrict the u function further. Now, let us define a process MT. So this is the process that will help us to transform the probability distributions from the probability law with beta theta to the probability law with u and alpha. So what is MT? And from the symbol itself, you can guess that basically we are trying to construct a martingale. So MT is exponential of these two, sum of these two things. So minus u dB, integral u dB minus half integral u squared ds. So MT is our agent of transformation, which will help us in creating the right kind of probability. Suppose the probability law of y is denoted by P and it has a density dP. We are assuming that it has a density so that we can do explicit calculations. Now define a new density dq or a new probability law q through this relation. dq is mt dp. So mt we have written down here explicitly. dp is coming from y, some probability law. So a new probability law is created, dq as m into dp. And I think now you can see the connection with something that we have discussed earlier immediately. So then construct b hat as a new Brownian motion defined as integral uds plus b. So basically b hat is driven by db hat equal to uds plus db. So this is like a adding a trend part or changing the mean. So b hat is a new Brownian motion with respect to the probability capital Q. Q is defined as in here. And in terms of b hat, this new Brownian motion, the process y can actually be represented like this. So what am I doing? I started out with the original representation of the process y as beta dt plus theta dB. It is an Ito process, no problem. Then what I do is I transform both the trend and the volatility coefficient using this connection, this relationship with some restrictions. I also transform the probability law. So this was in terms of dB, the original Brownian motion. So I change the probability law by multiplying the density with this expression mt as defined here. So I knew probability law is dq equal to m dp. And I also transformed the Brownian motion to a new Brownian motion b hat, which is after adding a trend. Then I say that the same dy, the same process y, etho process y, can now be expressed as follows. Dy is alpha dt plus theta db hat. So what happens is, I wanted to transform the trend and the diffusion. This is what we do for standard normal. We start with a normal mu sigma square, and our target would be normal 0, 1. But in general, I can always do it in a different manner. I can go from normal mu sigma to normal mu 1 sigma 1. So this is what this Girsanov theorem is about. So I can change the trend and the volatility coefficient, of course satisfying this relationship. It cannot be inconsistent. This becomes an etho process with respect to a new Brownian motion. This new Brownian motion is adding a trend term to the original Brownian motion, and the probability law for this new process is now this q rather than the original p. So we have changed three things. We have changed the Brownian motion itself, we have changed the probability law, and we have changed the trend and volatility coefficient. Of course, these changes are all related to each other in a consistent way, so that now let us think about application. I can actually choose the alpha and u suitably, so that I want to redefine my etho process with a new and targeted trend and volatility. I have a target trend and volatility, but that will of course change the probability law. So that probability law change I can explicitly compute using this theorem. I know how the probability law is changed, and this multiplier is explicitly computed. So is this result clear so far? Because of course I am just making a statement of a theorem which has a very long proof. This is actually quite a complicated theorem with a long proof. If you want to look at the proof, in fact looking at the proof would be interesting. Oxendall, the book that I referred earlier, has 3 versions of this proof. And these 3 versions are actually to highlight different kind of interpretation of this result. So the same result has been proved 3 times using 3 different approaches to highlight 3 different interpretations of this result, which is beautiful, I thought. So I'm not going to ask you any detail of this proof later on, but I hope you will take a look at the proofs, all these 3 versions from Oxendall, because it's a very nice exercise. And of course, you understand that this is related to the Radon-Nikodym derivative in the usual measure theory. So this is the stochastic process version of the Radon-Nikodym derivative. And in addition, because we are working with only etho processes of a particular, we have a particular form, we can do explicit calculations. We can explicitly find the change measure as well as the new Brownian motion. Let me look at 1 or 2 examples, and then probably we can think about whether this makes sense. So again, suppose we have this 2-dimensional process y. This is a reasonably easy example where dy is given by the first row is 2 dt plus db1 plus db2. The second row is 4 dt plus db1 minus db2. So of course db is also 2-dimensional. So basically I have 2 sources of uncertainty. The first one is sum of the two random parts, and the second one is the difference of the two random parts. Trend is 2 and 4. So that is my dy. So I know what is beta and theta. So my beta is exactly this column here, and theta is this 2 by 2 matrix here. Now, what we are usually interested in is to make these things mean zero. So normally in statistics, we work with this kind of transformations to make the random variable zero mean. So what I really am interested in is to make this new trend, which is alpha, to be equal to 0. Because that's our typical application. So that's what we try to do here. So let us try to choose alpha equal to 0 and the corresponding u. I know this relationship will hold. So theta u will be beta minus alpha. So if alpha is 0, then the u will be essentially, what will u be? Am I going to divide by theta? So I want to solve u here. So what will I do? So did you follow this example so far? That I have this y process 2-dimensional and I want to make it mean 0, and in the equation here, if alpha becomes 0, then the equation is just theta times u equal to beta. So how will I solve for u? I have to solve for u. So beta by theta in some sense. What do I do?
So this is just a two variable in two equations, linear equations.
Two variable, two equations. So I can actually this is non-singular, so I can take an inverse. I'll just do the inverse. So this is the equation, pair of equations here. So this is a simple pair of equation, and I can solve. I can find u1 equal to 3, u2 equal to -1. So the new drift, this u will be given by 3 and -1. So u is 3 and -1. So again, the scan has been very bad here. So I will just hope that you can see it. You all have it in your Google Drive, so maybe you can open it on your computer and look at it better, because this is quite faint. So my u is 3 minus 1. I started out with 2, 4 and this thing. Now I have this u as 3 minus 1 because I wanted alpha to be 0. Now, of course, once I have u, I can immediately compute mt, because mt is my probability change measure. So mt will be this exponential of this integral sum. U square is defined as in cross product. So whenever we are looking at more than one dimension, then of course I have to make sense of what is u square. So that will be like u prime u. So I know that is just simply 10. That is easy. So my mt, as in here, will be given by 3 dv1 minus dv2, because u is 3 minus 1, minus half integral 10 ds. And if I do the simplification here, I will get e to the power minus 3b1 capital T plus b2 capital T, because this integral has nothing but constants, minus 5 times t, so 10 by 2. That's relatively straightforward because the coefficients have been all chosen to be constant. So this is my mt. The mt is explicitly computed, quite simple. So dq will be mt times dp. So I know exactly what dq, the density, new density will be. in terms of the old density. The old density have to be multiplied by this thing. The new Brownian motion also has to be added term, the added trend here with the original Brownian motion. So B hat t will be integral u ds plus bt, which means dB hat will be this trend part plus dB. So I write it in the differential form. In the differential form, it will be 3 minus 1 dt dBt. So I have the final complete answer. What is my answer? I know that the new process, the new representation of the process will be now theta dB hat, because alpha is 0. So dyt will be just theta dB hat. Theta, we know exactly how it looks. So the new process dy will be represented by simply this theta times dB hat, where of course dB hat is redefined with this trend. So the trend is sort of absorbed in B. Accordingly, the probability law has changed from capital P to capital Q. Now, because there is no trend here, with respect to dB hat, there is no trend. So this process has become a martingale. So I have essentially transformed it to zero mean. So it will become, it becomes a martingale. And the Q that we have defined here through the dq equation, this expression here, dq, this is the unique equivalent martingale measure. So for the process Y, I started out with the natural probability P. Then I did the transformation to make it mean 0, to make it a martingale. This is, remember, for the efficient market, this is what we do. We try to create martingales. So Girsanov's theorem is actually our toolbox to create martingales out of any origin, any initial choice of model with any initial choice of probability. So I started out with a dy and a probability P. I do the suitable transformations in order to make the process a martingale with respect to the new Brownian motion and the new probability law. So the new Brownian motion is actually absorbing a trend part. The new probability law can be explicitly computed using that, and that is actually unique. And that is the equivalent martingale measure that we have earlier simply mentioned somewhere. For the discrete setup, we have done this explicitly, the state price density expression that we have done explicitly for discrete setup. For the continuous setup, we did not talk about it explicitly. And this is the theorem that gives us the toolbox to compute the equivalent martingale measure. So now I will go back to the top. So Girsanov's theorem is essentially a way of creating zero mean random variables for our stochastic process language. Girsanov's theorem is a toolbox for creating martingales. Why do I need martingales? I need martingales because in the efficient market, if I can create a martingale, I can always create the corresponding no arbitrage portfolio, do the calculations in a simple way, and so on. Because I know that if it's a martingale, then it has got certain properties imposed on it by the market efficiency considerations. For the discrete setup, we did that using the state price density. We could do it explicitly because it was a finite state situation. For the continuous setup, we have mentioned this earlier, that if we can get a martingale, then such and such properties follow. But how to explicitly get that martingale, we did not do anything about it yet. So Girsanov's theorem is that important connecting piece where, starting with any non-zero drift, beta can be any function, non-zero drift, I create a new representation of the same process. The process is not changed. The representation has been changed by changing the Brownian motion I am working with. So with the new Brownian motion and under the new probability, I make dy a martingale. And this new probability can be explicitly computed, at least for simple enough situations. And that is called the equivalent martingale measure. Because under equivalent martingale measure, my change processes are martingales. That's what we have been talking about time and again. Now, questions.
Sir, can you give any intuition about why this Q should integrate to 1?
Why this Q should be?
Integrating to 1, because it is a probability density, dq, this one.
Oh yeah. So it is not about intuition. So you have to show, you can show it explicitly. You can
Yeah,
show
but
that
there is one factor that is like multiplying. So
multiplying, yes.
so this is just an analytical result that this is
This
a
is an
probability.
analytical result. Absolutely. This is an analytical result.
Okay.
But this analytical result has been scaled. You see, if you look at the expression for MT, so there is a deliberate half here. So this has already been scaled so that the integral equal to 1 will still hold. Otherwise, it is not a probability, correct?
Yes,
That's
sir.
what you wanted to ask.
Yes.
How do I know that actually dq is a proper probability density? So the integral is still 1. But it is scaled appropriately.
Okay, sir.
So that's why I wanted you to see the details of the proof, because in the proof, this is not the main part. This is an important part, but the main part is different. But if you look at the proof, or the proofs, there are 3 versions, as I said. The proofs will actually tell you exactly what is being done for what purpose. So I'm starting from a certain situation. I want to get to a new situation, which is more convenient for me, and exactly the path that I take. So the 3 proofs are essentially 3 different paths. So they give you different intuitions about this transformation process. So it's actually very illuminating to look at the proofs.
Okay, sir.
So if you want to discuss the proofs later on, then I'll be happy to discuss. I did not put it in this material because it is not an explicit part of the syllabus, because they are involved and quite complex proofs, but they are, as I said, extremely informative. So Girsanov's theorem is our last result, and this in the standard probability is just standard normal creation, creating a normal 0, 1 random variable. In measure theory, this is the Radon-Nikodym derivative process. In our Ito process setup, this is the stochastic process version with the additional advantage that I can do explicit calculations. So Girsanov's theorem not only says that things exist, etc., it also gives you the explicit formula to be able to compute the martingale. So I can explicitly find this martingale. I can make alpha equal to 0 under Q with respect to the new Brownian motion B hat. And you see, once you start thinking about it more deeply, you might start feeling a little bit confused that where did I eliminate the trend? Because the trend was there. So it is in the nature of the process Y. So how did it vanish? Remember that it did not vanish. It has been subsumed in the new Brownian motion. So the Brownian motion is actually absorbing the trend part in a very clever manner. So the new representation looks clean of the trend. The representation, as we get here, looks clean of the trend. It is only a martingale, but the devil is in the detail. because I have created a new B hat, that B hat has actually taken care of the trend part. So any other questions? So basically my teaching part, my lecturing part, I will say, not the teaching part, my lecturing part is done. The remaining classes, there will be 4 special lectures as we have already announced. Wednesday, we will have the lecture on regime switching models by Professor Anindo Goswami, who is from IISER Pune. And then Monday evening, there will be a class on Levy processes by Sudeep Chandra. That is the next probability model after the Ito process, where I have discrete jumps. And the 2 remaining lectures will be on more specific models by there will be Professor Indrelin Sengupta talking about Barndorf, Nielsen, Shepard model, which is essentially building on the Levy process. And Shubhajit Bishwas will be talking about variance swaps. So I did not discuss a lot about variance swaps. I just mentioned them in the presentation. So he will actually talk about it in more detail. So otherwise, there are no more lectures from me. What we will do subsequently is, after these special lectures are scheduled, we have the other sessions which are now empty. So I'm not scheduling classes really, apart from the special lectures. But once you start reading, once you start working on the exercises, the examples, and whatever you have not been doing so far, but I have been asking you to, you will let me know, and we can always schedule interactions. And I guess now some of the classes are being dissolved, so interaction timing is flexible. So whenever you think will work for you, we can schedule that. All right. So if you want to ask me anything, you can do that. Otherwise, we will close our class today.